Hey guys, this is Mrs. Harbin, and we are starting section 5.8, the end of Unit 5, Trigonometric Equations. Our biblical integration for this unit is that God allows us to have challenges in life, but He also equips us to face them. Becoming familiar with useful terms is like putting on armor to face algebraic problems. So in everything that you learn how to do in life, you're going to have to learn the foundational pieces. And by learning those foundational pieces, you're then equipped to face more difficult problems. And trig is exactly the same way. By learning these basic identities and how to apply them, you'll be able to solve more challenging problems. Our lesson objective for today is that you will solve trig equations on the interval 0 to pi. Now, if you remember our unit circle, one time around the unit circle is equal to 2 pi. 0 all the way around to 2 pi. Because trig functions are all periodic, we could keep going 2 pi, 4 pi, 6 pi, 8 pi, but we're only going to worry about the first time around the unit circle as we identify these different values of x. To solve a trigonometric equation, you may use identities or any of the algebraic techniques that you have learned. And all the examples that we're going to do today, we're typically going to start with an algebraic technique first and then use a trig identity. There are a few that we have to use a trig identity first before we use some algebra. But we're going to follow this basic process. First, we're going to solve for the trig function. So sine x equals, or tangent x equals, or cosine x equals. So we're going to rewrite the equation in terms of a trig function. Then we'll use inverse operations to find the actual value of x. So let's take a look at example number 1. We have tangent x minus square root of 3 equals 0. And we already have one single trig function here, so there's nothing we really have to do as far as trig identities go. So we're just going to use our algebraic steps that we already know. We need to isolate the tan x. So the way that we do that is by adding square root of 3 to both sides. When we do that, we get tan x equals root 3. Now we're going to use inverse operations to undo this tangent and get the x by itself. So the inverse of tangent is inverse tangent. If we take the inverse of one side, we're going to do that to the other. Okay, the inverse tangent of tangent x, these two cancel each other out, so we're just left with x. And then we need the inverse tangent of root 3. Remember that inverse trig functions are read this way. The angle whose tangent is root 3. So x is equal to the angle whose tangent is root 3. Now you're probably going to have to refer to unit circle because I want you to leave this in radians. I don't want you to write it for me as a decimal plugged into your calculator right now. So if we were to look on our unit circle, we would say the angle whose tangent is root 3 is pi over 3. That's in our first quadrant. But if we don't limit our domain to 0 and 2 pi, then we have to add this little piece here. That means constant times pi. Because tangent functions are periodic, like all trig functions, then we have multiple angles whose tangent is root 3. We have pi over 3, 4 pi over 3, 7 pi over 3. All of those angles have a tangent of 3. So we indicate that with this little constant times pi, because tangent repeats every pi times. 1 pi, 2 pi, 3 pi, 4 pi. That tangent value repeats. So we need to add that because we have not limited our interval here. Okay, k is going to represent then all the integers, how many times it repeats, every 1 pi, 2 pi, 3 pi, etc. For all the rest of our problems, though, we're going to specify a specific interval, so we don't have to worry about that little piece there. Just a reminder, because of the periodic nature of trig functions, there will typically be infinitely many solutions, and the way that we can restrict our solutions is by restricting it to the primary solutions in the interval x is greater than or equal to 0 and less than 2 pi. So we're going to restrict our answers here to those primary solutions, basically the solutions in the first time around the unit circle. All right, let's take a look at this example. Let's solve 2 cosine squared x plus 3 cosine x plus 1 equals 0. Hopefully, this reminds you of a quadratic function. This looks like 2x squared plus 3x plus 1 equals 0. And because that looks like a quadratic, it's actually going to act like a quadratic. So if we were to solve for an x, over here in our quadratic equation, we would factor that, set each of our factors equal to 0 because of the zero product property, and solve for x that way. Well, we're going to do exactly the same thing. We're going to go ahead and factor that, and when we do, instead of 2x plus 1 times x plus 1, we're getting 2 cosine x plus 1 times cosine x plus 1. So it's like we've just substituted cosine x for our x here. We'll then take each of those factors and set them equal to 0. And when we do that, we get cosine x equals negative 1/2, or cosine x equals negative 1. Now to find the exact value of x, we're going to take the inverse cosine of both sides. So we have the inverse cosine of negative 1/2, which we're going to read as the angle whose cosine is negative 1/2, or the inverse cosine of negative 1, which we'll read as the angle whose cosine is negative 1. Referring to a unit circle, we see that there are two possible values that have a cosine of negative 1/2 within our unit circle, 2 pi over 3 and 4 pi over 3. And we see that there's one value where the cosine is negative 1, and that's at x equals pi. So these are our three answers. X is equal to 2 pi over 3, 4 pi over 3, or pi. If more than one function appears in an equation, you're going to try to express all of these functions in terms of one trig function, or we'll have to separate them by factoring. So we're going to use our identities at this point first before we do any algebraic steps. So let's solve sine of 2x equals cosine x. Again, on this interval, 0 to pi. Well, I can't rewrite sine in a way that has cosine in it. They're not reciprocals or quotients or anything like that, but 2 sine x is one of our double angle identities. So we can rewrite 2 sine x as 2 sine x cosine x minus cosine x. Okay, so 2 sine x we rewrote as 2 sine x cosine x. And then we subtracted cosine x from both sides. Now we have two different terms. And when we did this live together, you guys knew we couldn't subtract cosine x from this cosine because the whole term was sine x cosine x. So we do have two terms here. Now that we have two terms, we look at what they have in common, and we notice that we can factor out a cosine x from both terms. So when we factor out a cosine x, we get 2 sine x minus 1 equals 0. At this point, we take our two factors, just like we've done before, and set them equal to 0. Using our zero product property, we get cosine x equals 0, or 2 sine x minus 1 equals 0. Go ahead and let's simplify that a little bit more. On the right-hand side, we get sine x equals 1/2. And now we're going to use our inverse cosine and our inverse sine to solve for x. Okay, the inverse cosine of x, it's the angle whose cosine is 0. We get pi over 2 and 3 pi over 2. And inverse sine tells us the angle whose sine is 1/2 gives us pi over 6 and 5 pi over 6. Again, refer to that unit circle. Hopefully you have yours handy. If not, you can look online for a unit circle, or just at the beginning of every time that you do homework, write that unit circle down for reference. All right, let's take a look at example 4. We want to solve 3 cosecant x minus sine x equals 2 over the interval x is greater than or equal to 0 but less than 2 pi. So on that first turn around the unit circle. Now looking at this, I notice that I have two trig identities, cosecant and sine. But I know because of my reciprocal identity that I can rewrite cosecant as 1 over sine. So I can rewrite that as 1 over sine, and then I can simplify that. 3 times 1 over sine x is just 3 over sine x. So this is simplified as this. So I have 3 over sine x minus sine x equals 2. I then want to get rid of my denominator here. And just like all other algebraic equations, when I want to get rid of the denominator, I multiply the whole thing by that denominator. So we're going to multiply this whole thing by sine x. When we do that, we get 3 minus sine squared x equals 2 sine x. When you multiply sine x times sine x, there are two different ways to write it. You can put it in parentheses and write sine x squared, or you can write it as sine squared x. Those are the two possibilities there. you're not going to write it as sine x squared. Because what that says, it's the sine of x squared. And that's not what we're finding. We have this identity, this sine x, and that's what we're squaring. So 3 minus sine squared x equals 2 sine x. Again, this should look like a quadratic. We have a square term, a linear term, and a constant. So we're going to rewrite that all on one side in descending order, sine squared x plus 2 sine x minus 3. And then we are going to factor. If we use some substitution, we could say that this is u squared plus 2u minus 3. I'm just using u instead of x here. And then we would factor that accordingly. And we can substitute that back in just a second. So when we factor, we get sine x minus 1 times sine x plus 3 equals 0. Using the zero product property rule, we'll set both of those equal to 0. So sine x minus 1 equals 0. When we simplify that, we get sine x equals 1. Or sine x equals negative 3. Using inverse sine, we want to find the angle whose sine is 1. And we get x equals pi over 2. And then using inverse sine x, inverse sine of negative 3, there isn't an angle whose sine is 3 or negative 3. Remember that sine ranges from negative 1 to 1. Remember when we did all those graphs of the different functions, its range was 1 and negative 1. So there is no angle whose sine is 3 or negative 3. So we only have the one answer there. X equals pi over 2. All right, let's move on to example 5. But a quick note, you can introduce extraneous roots when multiplying an equation by a trig function or when squaring both sides of an equation. So remember that when you finish, you do need to check your roots, check your answers, because you may have introduced an extraneous root, you may have introduced a root that does not work. Be sure to check your solutions. So let's take a look at number 5. We're going to solve cosine x plus sine x equals 1. And again, we're restricting here our interval between on the 0 to pi interval. Now, factoring doesn't separate sine and cosine. There's nothing that we can factor out because this is one thing and this is one thing. So we can't just factor out the x. We can't separate those. However, let me write that here. If I subtract cosine from both sides, I get sine x equals 1 minus cosine x. Well, that should remind you a little bit of the Pythagorean identity, except for the Pythagorean identity has squared terms. So what happens if I square both sides? We have sine equals 1 minus cosine x. We're going to square both sides, and that way we'll have the Pythagorean identity. So squaring this side gives us sine squared x, and squaring this side gives us 1 minus 2 cosine x plus cosine squared x. All right, sine squared x, according to the Pythagorean identity, we can replace with 1 minus cosine squared x, and now everything is written in terms of cosine squared. From here, we're going to combine like terms, and we get 2 cosine squared x minus 2 cosine x equals 0. At this point, we can go ahead and factor out what they have in common. Both of those terms have a 2 cosine x, so when we factor that out, we're left with a cosine x minus 1 in parentheses. We'll then set each of our factors equal to 0 because of the zero product property. So cosine x equals 0 or cosine x equals 1. Okay, using our inverse properties there, the angle whose cosine equals 0 and the angle whose cosine equals 1, we get 0, pi over 2, and 3 pi over 2. Let's go ahead and check our roots. We did have to square both sides earlier, and that means we have a possibility of some extraneous roots. So let's check our work here. And when we plug this back in, we find out that 3 pi over 2 does not work. It is extraneous. So our two solutions are 0 and pi over 2. Right, I do have one more example here, but I am quickly running out of time. So we'll take a look at this one in class. Instead of on the video, we'll start with this one tomorrow. If you guys have any questions, be sure to ask us.